All right, let's dive right into this explainer. Today, we're tackling a fascinating new paper that addresses a massive, glaring elephant in the room. Why is it that incredibly smart AI agents still hit this frustrating performance ceiling when you actually put them into production? Well, we're going to unpack the mechanics behind reinforcement learning-based, self-improving LLM agents.
So let's start with a really basic but crucial question. Why do the smartest AI agents still repeat the exact same mistakes? Basically, right now, current LLM agents are living in the movie Groundhog Day. I mean, if they face the same complex task, they're going to make the exact same mistake. Why? Well, because their underlying weights are totally frozen at inference time. They literally do not learn from their failures during deployment.
But here's where it gets exciting. This paper introduces a brilliant workaround. It's a reinforcement learning, or RL framework, that allows these agents to self-improve based on scalar rewards, basically simple numerical feedback. And they do this without requiring expensive full model retraining. We're talking about continuous optimization without rewriting the language model's fundamental weights. The bottom line, your AI gets smarter on the job, and you don't have to foot the bill for a massive server overhaul. Okay, here's a quick look at our roadmap. We'll start with the static AI problem, explore the self-improving solution, look inside the RL framework, break down the accuracy, efficiency, and cost, see how it crushes the benchmarks, and wrap up with the future of agents.
Section 1. The static AI problem, or what we're calling the Groundhog Day trap. Right now, the core architecture of pretty much all deployed LLM agent frameworks relies on a fixed inference time policy, and that comes with some serious limitations. Inference is just a fixed, deterministic process. There's no built-in mechanism to record outcomes and actually improve from failures. Because the prompt, the tool calling, the output parsing, none of it ever adapts based on past successes or failures, the errors just compound. If you're running a multi-step task, like a multi-month scientific literature synthesis, that compounding effect can cause a catastrophic failure. Now, sure, there are verbal feedback systems out there like Reflection, but they totally lack formal reinforcement learning convergence guarantees.
Now, you might be wondering, okay, but what about RLHF? Reinforcement learning from human feedback uses scalar preference feedback from humans to boost model alignment. But here's the catch. Traditional RLHF is essentially like doing open brain surgery on the AI. It demands massive compute. We're talking something like 800 GPU hours just to fine-tune a model like GPT 3.5 Turbo. That makes it completely unfeasible for continuous online deployment where you really need an agent to just adapt on the fly.
Section 2. A self-improving solution. Medication over surgery.
So instead of that crazy expensive surgery, the researchers propose a frozen weight architecture. Think of a static agent. Fixed inference, no learning. Literally repeats identical errors. Contrast that with this new RL agent. It features dynamic inference, learns from scalar rewards, and continuously optimizes its own policy. By training a super compact policy network right on top of a frozen model, this approach is kind of like giving the AI daily vitamins to perform better over time, rather than putting it under the knife for that invasive brain surgery we just talked about.
Section 3. Inside the RL framework, the architecture of improvement.
Okay, let's look at the learning loop, because it's a beauty. Step 1. A task planner. Think GPT-4 or Llama. Processes the user query. Step 2. An episodic memory module retrieves past state action pairs. Step 3. An actor-critic policy network selects an action. Step 4. The environment returns a scalar reward. And finally, Step 5. Proximal policy optimization, or PPO, updates the network. This creates a really tight loop where the agent systematically optimizes its expected rewards over time. It's essentially learning a formal rulebook for what actions lead to success. It's a lot like how a human learns through trial and error, honestly.
Let's actually zoom in on Step 2 for a second, that episodic memory module. This is a ring buffer that stores the 512 most recent state action reward tuples. It uses cosine similarity to retrieve the top 5 most similar past states and prepends them right to the task planner. What does that mean in plain English? Basically, this memory module drastically cuts down early exploration costs by pulling up past successes as experience demonstrations. It immediately points the agent in the right direction based on what actually worked before.
Section 4. Accuracy, efficiency, and cost. De-jargoning the math.
Now, the math behind this might look a little intimidating at first glance, but it's really just a conceptually simple business balancing act. The composite reward function automatically calculates a score based on 3 variables. A is task accuracy, weighted heavily at 0.6, so getting it right. E is execution efficiency, weighted at 0.3, doing it fast, and C is operational cost, weighted at 0.1, keeping it cheap. This automatic calculation perfectly balances getting the right answer, reducing redundant debugging loops, and minimizing those expensive API token expenditures. And it does all of this without a human ever having to manually grade it.
Section 5. Crushing the benchmarks, proving the disruption.
So to prove this actually works, the researchers threw this system against some truly brutal coding and math benchmarks, Human Eval, GSM 8K, Hotpot QA. And the results? A massive leap in task accuracy. Your standard static agent sits around 82%. A memory-augmented agent bumps up to 90%. But look at the RL agent, 97%. It absolutely crushes the standard agent by 15 percentage points, and it completely dominates exact match numerical tasks on the GSM 8K math benchmark in particular.
And it's not just more accurate, it is way faster. The learning efficiency jumps to 95%. This proves the agent literally stops wasting time. For example, on the Human Eval coding benchmark, the RL agent drops down to needing just 1.3 debugging iterations, compared to the standard agent, which fumbles around with 2.8 iterations.
But you have to ask, how do we make sure it doesn't learn the wrong things? Well, the system remains stable because proximal policy optimization, or PPO, clipping, keeps the updates within a safe trust region. That prevents any wild, destabilizing jumps in behavior. Plus, they added an entropy bonus, which stops reward hacking. Basically, it prevents the AI from cheating the system by just blurting out the right answer without actually showing the required reasoning steps. And finally, a trajectory quality filter acts as a bouncer, preventing low-quality episodes from contaminating the memory buffer.
But honestly, the most mind-blowing part of all of this is this number right here, 10 to 12. It only takes 10 to 12 training episodes, which is roughly just 1,000 to 1,200 task instances, to hit that near-optimal 97% accuracy. That is unbelievably fast for an agent that is literally teaching itself in a live deployment environment.
Section 6. The future of agents, scalability, and beyond.
Because this convergence happens so incredibly fast, we have to talk about what this means for rolling these agents out into high-throughput, real-world business environments. First up is scalability. The research shows that scaling action spaces up to 64 discrete actions yield some highly favorable cost benefits. The actor network scales linearly. That means we can give the agent up to 64 complex tool actions, things like web searches, code debugging, database queries, with only an 18% increase in training time.
So, what is next for RL agents based on this framework? Well, future applications could easily see teams of specialized agents sharing their memories through a common experience replay buffer. Or we could see the use of smaller, locally hosted models, like a Llama 7B or 13B, to drive that already impressive 1650 millisecond latency down even further, practically slashing API costs to zero. And there is just massive potential for transfer learning, where an initialized policy network is seamlessly transferred across entirely new enterprise domains. As the authors of the paper put it so well, the proposed framework obtains much higher final accuracy with no fine-tuning compute cost and can continue to improve during deployment, reaching 97% after just 12 online episodes. That statement brilliantly summarizes the massive commercial advantage of inference time policy learning over those traditional, expensive weight modification techniques.
Which leaves us with this final thought. If an AI agent can literally self-improve in a matter of hours without a single model weight update, what does that mean for the shelf life of traditional fine-tuning? It really makes you wonder. As agents learn to adapt dynamically, right there on the fly, are we witnessing the end of static AI models as we know them? Thank you so much for joining me on this explainer. Keep questioning, keep learning, and I'll catch you on the next one.